Okay, so hi everyone. So welcome back to the third video in this playlist. So today in this video we are going to solve this problem from CSES problem set that comes under the tree algorithms part and goes by the name tree diameter. So let us start with the problem now. But before starting this video, if you are new to this channel and have not yet subscribed it, then I will suggest you to subscribe this channel, as there is a lot of amazing content related to competitive programming topics is already uploaded here, right? So yeah, if you have not yet subscribed it, consider subscribing the channel and share with your friends who need to watch these videos. So let us get back to the problem now. So the problem reads like this, that you are given a tree of n nodes. So you will be given a tree, and the diameter of a tree is the maximum distance between any two nodes in that tree. So here is the definition of diameter given. So our task is to determine the diameter of the tree. So the problem is asking you a simple thing, that for a given tree of n nodes you have to find the diameter. And what is the diameter? It is the farthest distance possible between any two nodes in this tree, right? So in the input you will be given an integer n representing the total number of nodes in the tree, and the nodes are numbered from 1 to n, right? And then there are n minus 1 lines describing the edges, and each line contains two integers a and b. That is, there is a bidirectional edge between nodes a and b. And in the output we just have to print the diameter of the tree. So these are the constraints here, in which the value of n can go up till 2 into 10 to the power 5, and the value of a and b can go up till n, right? So this is the input given here, and this is the expected output here, right? So this is the overall question. Since it is asking us to find the diameter, so that's why I won't complicate it, and I will tell you the exact stuff approach how to solve this. So actually there are two methods to solve this problem, that is to find the diameter. The first approach involves a double DFS call, and the second approach uses a single DFS call. But since the constraints here can go up till this, so that's why the double DFS call will also work approximately in the same manner as the single DFS call, right? So in this video I will just be telling you the double DFS call, and that is more intuitive and beginner friendly, right? So since in the input here the input is quite small, right? So to make you guys understand better, I will consider an example by myself, and using that example I will tell you how to calculate the diameter of the tree. So let us go to the blackboard now. So consider this tree that I have drawn by myself here, right? So our goal is to find the diameter of the tree, right? So let me write the definition of a diameter here. So what do you mean by diameter? So diameter is nothing but the farthest distance between any two nodes, right? So if this is the definition of a diameter, and this is our tree, and we want to find its diameter, we want to find those two nodes between which the number of edges are maximum. If we pick any two nodes randomly, let's say we pick this node here, and let's say we pick this node, that is 10 and 5, then what is the distance between them? So in order to calculate the diameter, we take each edge as a distance of 1, right? As a distance of 1 unit. So between the nodes 10 and 5, I can say that the distance between them is this path. So the distance is equal to this 1 plus 1 2 plus 1 3 plus 1 4 plus 1 5 plus 1 6, because this is the path between 10 and 5, right? So the distance between 10 and 5 here is 6. This is how we calculate the distance between two nodes in a tree when the edge weights are not given and we want to find the diameter only, right? In order to find the diameter, obviously we want to select those two nodes between which the distance will be maximized. So the first thing that you must understand is that those two nodes between which we are trying to find the diameter are nothing but the leaf nodes, right? And I want you to think about it, why those two nodes will be the leaf nodes, because these leaf nodes will be present at the extreme bottommost points of the tree, right? So now we know that those two nodes can either be this or this or this or this or this or this. So if I write those potential nodes here, then those nodes can be either this 10 or this 17 or this 16 or this 18 or this 8 and then 5 and then 7. So these are our leaf nodes, right? So a total of 1, 2, 3, 4, 5, 6 and 7. So 1, 2, 3, 4, 5, 6, 7. So a total of 7 leaf nodes are present here. And between these leaf nodes only, we have to select 2 of them, between which the distance will be maximum. Got it? So how to do it? So our approach will be very simple. So since we want to find 2 different nodes, so let me draw here. So we want to find 2 different nodes, right, between which the distance will be maximum. So first what we will do is, first we will try to find the first node, and after we find the first node, then only we will think about the second node here, right? Okay, so how to find the first node? What I will do is, I will just call a simple DFS function from this root, and using the DFS function I will try to find the distance starting from this root node to each and every other node present in this whole tree, right? So if I do that, then I will be able to get the distance from this one node to each and every other node. So if this node is 2, then the distance from root is 1. If this node is 8, then the distance from root is 2. If the node is this 13, then the distance from root is this 1 plus 1 plus 1 plus 1, that is 4, right? So by doing that, I will be able to find the distance from this root node to each and every other node in the tree. And why will it help? It will help because out of all the distances in that distance array, we will select the maximum distance, right? And along with that, we will also have a record of the node which is having that maximum distance from this root node, right? And that node will become our first node that we need to find here. So as I said, we need to maintain a distance array here, right? So for now, let me erase this. We need to maintain a distance array. Let me quickly mark it. So since the total number of nodes present here are 18, so I need to create an array of size 19 here, right? So let me do that quickly. So now what I am telling you is to find the distance from this root node to each and every other node present in this tree, and you will very soon realize that how this will help us in order to find the diameter, right? So initially this distance array here that I have drawn is holding the value for each and every element equal to 0, right? So I have not written that digit here 0. Let us do it one by one. And also before starting, since there is no node with the 0th value, so let me cross it here so that you will only be focusing on the remaining part from 1 to 18, right? So now tell me, what is the distance between the root node till this 1? So the distance between 1 to 1 will be 0. So it will be 0, right? Similarly, what is the distance from this 1 to this 2? It is 1. And same for 3 also, right? Now what is the distance from 1 to 4? So the distance is 2, right? And what is the distance till 5? So the distance will include this path consisting of 3 units. So 3. What is the distance from 1 to 6? So the distance between 1 to 6 is just 2, right? What is the distance from 1 to 7? So 3 units. So 3. What is the distance between 1 to 8? So 2. What is the distance between 1 to 9? 2 only. What is the distance between 1 to 10? So 1, 2 and 3. So 3. What is the distance between 1 to 11? So 1, 2, 3. So 3. What is the distance between 1 to 12? So 1, 2 and 3 only. What is the distance between 1 to 13? So 1, 2, 3 and 4. So 4. What is the distance between 1 to 14? So 1, 2, 3, 4 and 5. What is the distance between 1 to 15? 1, 2, 3, 4. What is the distance between 1 to 16? So 1, 2, 3, 4, 5, 6. And what is the distance between 1 to 17? So 1, 2, 3, 4, 5. And what is the distance between 1 to 18? So 1, 2, 3, 4, 5. So this is the distance from the root to each and every other node present in this tree, as you can see. I have written here, right? So once I have calculated this distance array holding the values of distance of that node from the root node, so as I said that out of these possible leaf nodes, we have to select a node which will act as the one of the end points of the diameter. In order to do that, we will take help of this distance array now. So if you see in this distance array, then this 16th node here, right, this 16th node is having a value of 6. That is, this 16th node is having a distance of 6 from this root node here, right? So since this 16th node, which is a leaf node that I have written here also, is having a distance of 6, and it is the maximum among all the leaf nodes. So if you compare here, then the distance between this root node till this 10th node here is what? So it is equal to 3. So if I write here, then it is nothing but 3 here, right? And also the distance between 1 to 17 is what? So it is 5. And what is the distance between 1 to 16? So it is 6. And what is the distance between 1 to 18? So it is 5. And what is the distance between 1 to 8? So it is 2. And what is the distance between 1 to 5? So it is 3. And what is the distance between 1 to 7? So it is 3 only. So as you can see that out of all these distances from the root node to each and every possible leaf node here, and why we are focusing on leaf nodes only? Because the distance between the root node and a leaf node will always be greater than that of internal nodes that are present above those leaf nodes, right? So that's why we are only focusing on this leaf nodes only. And out of these leaf nodes only, we have to select two nodes that will act as the endpoints of the diameter. So as you can see that out of all these distances, the maximum is 6, which is for the 16th node, that is this node here, right? So what I'm trying to tell you here is this 16th node will act as our first node, that is one of the end points of the diameter, because its distance is literally very far from the root node, or the maximum from the root node. That is, it is present at the bottommost part of this tree. So that's why we are giving this 16th node here as one of the end points of the diameter here. And once we have found this node here, now we want to find the second node, right? And in order to do that, what I will do here is I will again call a DFS call starting from the 16th node, and through that it will find the distance from this 16th node to each and every other node present in this tree. So now if I do that, then the distance between 16 and 14 will become equal to 1, and the distance between 16 and this 12 will become 3. And like that we will be finding the distance between this 16th node and each and every other node in the tree. So till now we have found the one of the endpoints of the diameter, which is one of the leaf nodes and is present at the bottommost part of this tree, right? And this is obvious also. And once we have found that, we are now trying to find the other end of the diameter using this first end here. And that other end will be present at the maximum distance starting from this first node, right? So it should be very obvious to you that the other point of the diameter that we are trying to find, which is one of the leaf nodes only, will be having a maximum distance from this first node. That is one of the endpoints of the diameter that we have already found. So that other point will also be a leaf node, and it will be having a maximum distance from this 16th node, right? So that's why now we just want to find such a node that will be having a maximum distance from the 16th node, and that's why we are running a second DFS call from the 16th node, right? So in order to do that, let me copy this distance array again, right? And in this distance array, let me erase these values that I have written previously, because now we want to calculate a fresh distance starting from 16th node to each and every other node. Let us do that quickly. So if you now try to find a distance between this 16 to this one, then what it will be equal to? So it will be equal to 1, 2, 3, 4, 5 and 6. So it will be equal to 6, right? And what is the distance between 16 and 2? So it will be equal to 1, 2, 3, 4, 5. So 5. And what is the distance between 16 and 3? So it will be equal to 1, 2, 3, 4, 5, 6, 7. So 7. And what is the distance between 16 and 4? So the distance till 3 plus 1. So 7 plus 1, 8. And what is the distance till 5? So distance till 4 plus 1. That is 8 plus 1, that is 9. And what is the distance between 16 and 6? So the distance till 3 plus 1. That is 7 plus 1, that is 8. And what is the distance till 7? So distance till 6 plus 1, that is 8 plus 1, that is 9. And what is the distance between 16 and 8? So 1, 2, 3, 4, 5, 6. So 6. And what is the distance between 16 and 9? So 1, 2, 3, 4. So just 4. And what is the distance between 16 and 10? So 1, 2, 3, 4, 5. So this. And what is the distance between 16 and 11? So 1, 2, 3, 4, 5. And what is the distance between 16 and 12? So 1, 2, 3. And what is the distance between 16 and 13? So 1 and 2. So 2 only. And what is the distance between 16 and 14? So just 1. Because it is the immediate parent of this 16. And what is the distance between 16 and 15? So 1, 2, 3, 4, 5, 6. And what is the distance between 16 and 16? So obviously it is 0. And what is the distance between 16 and 17? So 1, 2, 3. And finally, what is the distance between 16 and 18? So 1, 2, 3, 4, 5, 6, 7. So 7. So in this way, I have calculated the distance from this node, that is one of the endpoints of the diameter, to each and every other node present in the tree. And now, since we want to find the other end of the diameter, then we have to select such a node among these leaf nodes which will be having a maximum distance from this node, right? So if you see here, then the maximum distance among all such leaf nodes here, so if I write here, then so the distance between 16 and 10 is what? So it is 5. The distance between 16 and 17 is what? So it is 3. The distance between 16 and 16 is 0. The distance between 16 and 18 is 7. And the distance between 16 and 8 is 6. The distance between 16 and 5 is 9. And the distance between 16 and 7 is also 9. Right. So these are the distances between the first endpoint to each and every other leaf node present in the tree. And as you can see that the maximum distance is this 9, which is for this 5th node as well as this 7th node, right? So that's why I can say that the diameter of this tree is nothing but this 9 only, which is present between this 16th node and this 5th node, or between this 16th node and this 7th node. So there are two paths possible here. So if I draw that here, then it will look something like this. The path will start and go like this, right? So this is one of the diameter possible involving a total of 9 lengths. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Or what could have happened is we could have selected this path, right? So 1, 2, 3, 4, 5, 6, 7, 8 and 9. So this is also one of the possible diameter of this tree, as you can see. And this is the maximum you can get. And this is happening for the two extreme leaf nodes of this tree only, as you can see, and not any internal nodes. So this is the whole logic behind this problem. So what you have to do, you just have to see that among all the possible leaf nodes, what nodes you must select so that the distance between them is maximized. And in order to do that, what we did was we just found the first extreme node. And how we did that? We first calculated the distance starting from the root node to each and every other node in the tree, and by that we were able to find the bottommost or the farthest or the deepest node possible in the tree, which is our 16th node here. And then we again did a DFS call, that is the same DFS call, but at that time we started from the 16th node, that is the first farthest node. and again we calculated a distance to each and every other node, and that node which is having a maximum distance from this first farthest node will act as the second endpoint of the diameter, right? And the distance array having a maximum value will be nothing but our diameter, which is 9 in this case. So we just have to print a 9 here, and in this way this problem will be solved. So without wasting any further time, I think we should go to the code editor and code this up quickly, right? So let us go to the code editor now. So first you have to take the input for n, right? It is the total number of nodes in the tree, and then you have to take the input for the n-1 lines here, right? So I will do a 1 based indexing only, so from 1 to n-1 like this, right? And let's call these two integers between which the edge is present as u and v. So take its input and so take it properly, and using this u and v I will construct a adjacency list here. So g of u dot push back this v, and this g of v dot push back this u, right? So since the total number of nodes here can go up till 2 into 1e5, so let me declare the total number of nodes globally here as max n, so 2e5 plus 1, right? And let me also declare the adjacency list here, that is vector of LLG like this, right? So in this way our adjacency list is initialized, right? So now let us start our first DFS call here like this, and we know that since 1 is a root node, so we will start from 1 only, and we also have to pass its parent as -1 initially. So if I write this DFS call here, so it will be a void type, and this will be our node and this will be our parent, right? So we know how we used to do a DFS on a tree. We just need to iterate through each and every child of this node, that is for auto child belonging to the adjacency list of this node. If this child is not equal to the parent, then we will again call this DFS call, and this time this child will be our node and its parent will be this node. But I think there is some error, let me see. Okay, so this is a wrong bracket here that I have given, so it will be like this. So once I have written this, since we want to calculate the distance from this root node right now to each and every other node, so let me also declare a vector that is the distance array here like this, right? So I will call it dis t, or rather dis, and it will be of this max n size only, and initially each and every value is equal to 0, right? So we know how we used to calculate the distance, so let me tell you here quickly. So suppose we are present at this first node, and using recursion we know that it has two childs, that is this second and this third node. So when we will be moving to the second node, then we will know the distance we have took to reach the first node. Then the distance taken to reach this second node, that is the child, will be nothing but the distance taken to reach its parent plus 1, right? So the same thing I will write here. So since we now know here that we are moving from this node, right, to this child, so I will just say that distance for this child will be nothing but the distance we took to reach its parent, that is this node, plus 1, like this. And using this, the distance array will be calculated for the whole tree. And once the distance array is calculated, we now want to find the first farthest node using this distance array, right? So let me write here as the first farthest node as initially -1, and in order to find that I will iterate through this distance array. So I will iterate through its complete size, that is from 1 to n, and I will check that which node has a maximum value, right? And in order to do that, let me also declare a global variable here as, let's say, maxi, which is initially equal to 0. So if the distance for this ith node in the distance array is greater than this maxi, then I can say that our new maxi is this distance of I, and our first farthest node here will be equal to this ith node. And once this for loop ends, we will be having an information of this maximum distance from the root node and also the first farthest node, right? So once we have found our first farthest node here, we now know what we have to do. we again have to call the DFS function, right, starting from this first farthest node, and again its parent will be -1. But before doing that, please ensure that you have reassigned each and every value in this distance array for n+1 nodes equal to 0, like this. And why we need to reassign each and every value in this distance array equal to 0? Because we need to use this distance array again for this first farthest node, right? So instead of declaring a second array, we just want to utilize the same array. So that's why I have reinitialized it to its 0th state. So once this is done, so again we know that through this DFS call, it will calculate the distance from the first farthest node to each and every other node in the tree, right? And now in this second distance array that we have calculated, we have to again find the maximum value, right, which will be present at one of the leaf nodes only. So again, I will again run this same logic here like this, as you can see, right? So since I've declared maxi before, so that's why I don't have to declare it here again. So again I will iterate through all the nodes and I will check if this distance is greater than maxi. If it is true, then I will update my maxi like this. And once the maxi is calculated, we know that this maxi is nothing but our diameter only, right? So we wanted to calculate diameter and it is stored in this maxi. So this maxi is our diameter. So I will just print this diameter and return like this. So this is how we will calculate the diameter of the tree. And one thing should be visible to you here is that when we are doing the second DFS call from this first farthest node, then we just need the distance, that is the maximum distance. So there is no use of this statement anymore because we just need this maxi variable now. So I guess this is our solution here. So let us run and see if we are correct here or not. So as you can see that the test case is getting passed. So let me try to submit the same solution on the website here. So let's see. So as you can see that our solution is accepted completely, and this is the code that we just wrote. So yeah, this was pretty much about this problem. So thank you so much for watching this video. Thank you.